Have you ever wondered how limestone is turned into the white powdery substance called quicklime used in construction? That transformation is actually a chemical reaction, more specifically, a decomposition reaction. Let's explore what this really means. A decomposition reaction is a type of chemical change where a single compound splits into two or more simpler substances. It's like breaking apart a complex puzzle into its individual pieces. In chemistry, we represent this with the general formula A gives A plus B. These reactions are essentially the reverse of combination reactions, which are about forming compounds by combining elements. But here, we go in the opposite direction, breaking down. What makes decomposition reactions interesting is that they don't happen on their own. They require an external source of energy, either heat, light, or electricity, to overcome the stability of the compound. A classic example is heating calcium carbonate, written as CaCO3, which breaks down into calcium oxide, CaO, and carbon dioxide, CO2. So, every time limestone is heated in a lime kiln to produce quicklime, it's chemistry in action, a decomposition reaction unfolding with heat. Now that we know what a decomposition reaction is, let's look at its different forms because not all decomposition reactions happen the same way. The first type is thermal decomposition, where heat acts as the energy source. For example, when we heat red mercuric oxide, HGO, it breaks down into liquid mercury and oxygen gas. The reaction goes 2HGO gives 2Hg plus O2. Next, we have photochemical decomposition triggered by light energy. This is beautifully illustrated by the reaction of silver chloride, AgCl. When exposed to sunlight, the white compound turns gray as it decomposes into metallic silver and chlorine gas. The equation reads 2AgCl gives 2Ag plus Cl2. Then comes electrolytic decomposition powered by electricity. During electrolysis of water, electric current breaks water molecules into hydrogen and oxygen gases. That's 2H2O gives 2H2 plus O2. What's common in all these reactions? They all require an energy input to proceed. Without heat, light, or electricity, the compound would stay stable. And in each case, we are watching chemistry at work, transforming substances with energy. Let's dive deeper into the world of thermal decomposition, the type where heat alone causes substances to break down. This kind of reaction is widely used in labs and industries. Take zinc carbonate for example, ZnCO3. When heated, it decomposes to form zinc oxide, ZnO, and carbon dioxide gas, CO2. Simple enough, right? Now consider metal nitrates like lead nitrate. When you heat it, a more complex breakdown occurs. Two molecules of Pb open bracket NO3 close bracket twice, that's lead nitrate, decompose into two molecules of lead oxide PbO plus four molecules of nitrogen dioxide gas NO2 and one molecule of oxygen O2. You can actually see this happening in real time. Reddish-brown fumes of nitrogen dioxide emerge, while a yellow solid of lead oxide is left behind. This visual cue makes thermal decomposition reactions really striking in the lab. In real life, this process is used in lime kilns, where calcium carbonate is decomposed to produce quicklime, essential in cement and plaster making. These reactions aren't just textbook chemistry, they're the building blocks of the world around us. Have you ever looked at an old black and white photograph and wondered how light created that image? The answer lies in photochemical decomposition, where light energy breaks down certain compounds. One famous example is the decomposition of silver chloride, AgCal. In sunlight, this white compound transforms into gray-colored metallic silver and chlorine gas. The reaction is 2AgCal gives 2Ag plus Cl2. This change is visually striking. The white powder gradually turns gray as silver forms. This reaction was at the heart of black and white photography. The silver halide coated films would darken when exposed to light, capturing an image. So the click of a camera wasn't just mechanical, it was a photochemical reaction taking place at the molecular level. Even today, photodecomposition plays a role in photosensitive coatings and materials that react to sunlight. It reminds us how chemistry can freeze moments in time, literally through light. Let's now turn to electricity, a force powerful enough to split water into gases. Electrolytic decomposition uses electric current to break down ionic compounds, especially when they're in solution or molten form. The best known example is the electrolysis of water. When a small current is passed through acidified water, it decomposes into hydrogen and oxygen gases. The reaction reads 2H2O gives 2H2 plus O2. In the lab, you'll see this happen in a simple setup. Two electrodes dipped in water connected to a battery. Bubbles begin to form, more at the negative electrode, which is the cathode, where hydrogen gas is released, and fewer bubbles at the positive electrode, or the anode, where oxygen is formed. Why more hydrogen? Because the ratio is 2 parts hydrogen to 1 part oxygen, just like in water's formula. This experiment isn't just a classic school demo. It's used industrially to produce clean hydrogen fuel, a key player in green energy initiatives. So, through electrolysis, we are literally powering the chemistry of the future. Let's take a moment to bring it all together. Decomposition reactions are a vital category of chemical changes where a single compound breaks down into simpler products. These reactions always require some form of energy, be it heat, light, or electricity, to overcome the stability of the compound and initiate change. We've looked at three main types: thermal decomposition like CaCO3 breaking into CaO and CO2, photochemical decomposition like silver chloride decomposing into silver and chlorine under sunlight, and electrolytic decomposition such as water splitting into hydrogen and oxygen gases. These are not just academic reactions, they show up in photography, construction, metallurgy, fuel production, and more. The common thread is the transformation of matter using energy, and that's the beauty of decomposition. It helps us understand how things break down, evolve, and get recycled in the chemical world. I hope this session helped you see the invisible world of chemical change in action, from the crackling heat of lime kilns to the silent spark of electrolysis. Stay curious, and I'll see you in the next class with more fascinating chemistry.